Hello, in this video I will be using nonlinear and linear regression to show the relationship between vapor pressure and temperature for various substances. Specifically, in this example I will be taking a look at water. Now this relationship can be shown through what is known as the Antoine equation. Now this equation is a semi-empirical model and it can be shown as follows. Log base 10 of your vapor pressure equals A minus B over C plus T. Now as I said, P is your vapor pressure, T is the temperature, and A, B, and C are coefficients that are given to you beforehand and are specific to each substance that you're working with. Now in this example, I have been given experimental data for vapor pressure and temperature of water. And first I will be using nonlinear regression in order to determine the variables of A, B, and C. Now to do this, I will be using a coding software known as Colaboratory. But before we hop into that software, I would just like to give a visual of just exactly what is going on in these calculations. So first I will be plotting the data that I've been given. And on the x-axis will be our temperature. This temperature will be in kelvins. On the y-axis will be log base 10 of our vapor pressure. This vapor pressure is in pascals. Now when I plot this data, it will look something along the lines of this. After this, I will plot our model, which is the Antoine equation, and it will go through our data points and look roughly something like that. Now, as you can see, there is some difference between our data points and the model. Now, we want these differences to be as minimal as possible to get the most accurate values for our A, B, and C coefficients. In order to do this, I will be using a method known as the sum squared error method. And it goes as follows. We will take the sum of our data, starting from I equals 1, and going to n, our last data point. We have the log base 10 of our pressure. This is our data. Now what we'll need to do is subtract the difference between our data and the model. So we need to subtract our model from this. And our model is the Antoine equation, A minus B over C plus T. Now, as you can see, some of these deviations from the data in our model are negative. For example, this deviation right here, that is a negative deviation. Some of the deviations are positive. So this deviation right here would be an example of a positive deviation. Now, in order to make all of these deviations positive and account for the same amount, we will need to square this equation. Now, using the sum squared error method will allow us to get the most accurate values for our A, B, and C coefficients. Now I will be going into Colaboratory to write up some calculations in order to determine these coefficients.
Okay, so now that we are ready to set up a system in order to determine the coefficients of A, B, and C for our Antoine equation, what I will first need to do is get our experimental data into Colaboratory. So what I will need to do is convert this to a raw CSV file. I will then copy the link, and I will be using a command in Colaboratory called wget. And I will be pasting that link. And if we click Shift Enter, this will download that experimental data into Colaboratory. So if I check our files over here, I will notice that the water vapor pressure CSV file has been downloaded. So we are good to go. So next I will need to import numerical Python numpy as np. And I will be using a command within numpy in order to load our CSV file into this code. So I will do data, and the command is load text. And inside here I will need to enter the name of the CSV file. So water vapor pressure. Now I will also be using a delimiter of of commas here as well. Now, what I will need to do next is assign variables to our experimental data. Now, in the first column of our data is the temperature values in Kelvin, and the second column is the vapor pressure values in Pascal. So what I'll do is assign T to our temperature values, and since these temperature values are in the first column of our data, I will assign that to the first column. But if you can remember, Python syntax starts at 0 and not 1, so 0 is actually the first column of our data, so we are good to go there. And to assign our pressure values, I will take the log base 10 of these pressure values, because in order to make a correct graph of our data, remember we have to take the log base 10 of our pressure values. So I will do that when I am assigning the variable name. So I will use np.log10, and I will assign this variable to the second column of the data, so comma 1. So in order to make a graph of our data, what I will need to do is first import make subplots from plotly subplots. And I will also need to import plotly import output. So I will import that, and I will call that PO. Now, the first thing that I need to do when I am making a graph of our experimental data is set the rows and columns equal to 1, since they are one of each. So I will do fig equals make subplots, and then set the rows and columns equal to 1. Now, we want our data to be plotted as a scatter plot, so what I will need to do here is do fig.add_scatter, which will plot our data as a scatter plot. And I will assign the x values to the temperature and the y values to the log base 10 of our pressure values. So I'll do log equals, or x, or y equals log p, and I can do this, assign the y values to the log p, because our log p variable has already taken the log base 10 of all of our pressure values, so we are good to go there. Now I will set the mode as markers, and I will name this experimental data. So here is a plot of our experimental data, and we can tell that this is good, accurate data by looking at the boiling point for water. So if we look at 373 Kelvin and roughly 10 to the 5th pascals, we can see that this graph tells us that we have good, accurate data. So now what we'll need to do is minimize the error between our data points and our model, which is the Antoine equation. So in order to do that, I will need to define a function that takes in a vector of our parameters a, b, and c. So I will do define sum squared error, or SSE, and I will call that vector just v. Now next, I will need to unpack that vector into its fitted parameters that it will return. So I will do a, b, and c. And what I will need to do next is actually calculate the difference between our data points and the model, the Antoine equation, and square that, thus the sum squared error. So I will do return np.sum, and then take the difference between our data and the Antoine equation and square it. So I would do log p minus a minus b divided by c plus t. Now I will need to make sure that I square this. Now next I will be using a coded algorithm within Python that allows us to optimize and minimize functions. So I will need to import minimize from SciPy optimize. So I will do that. Okay. So now what I would need to do is minimize our function. So I would do minimize SSE, and we will need to have an initial guess for our parameters A, B, and C. So I would just guess 1, 1, and 0. So we can see that this worked correctly because I get a message that says optimization terminated successfully, and it gives us an array of 3 different values. So these values are actually our A, B, and C fitted parameters for the nonlinear regression. So what I'll need to do next is unpack this. I will need to assign this X array to this function and then unpack this into our A, B, and C fitted parameters for the nonlinear regression. So I will call these A and L to indicate nonlinear regression, B and L, and C and L. So now that we have those coefficients assigned, now what I'll need to do is plot our model, the Antoine equation. So I will do fig.addScatter. Our x values will still be temperature, however, this time our y values will be the Antoine equation with our fitted parameters for A, B, and C. So I'll do y equals ANL minus BNL divided by CNL plus T. Now, for this, I will set the mode equal to lines. And I will call this Antoine nonlinear regression. So do name Antoine nonlinear regression. So as you can see, our model fits our data pretty well. However, there is another way to do this example through the use of linear regression, which I will talk about next.
Okay, so like I said, there is another way for us to determine the A, B, and C coefficients of the Antoine equation by fitting our model, the Antoine equations, through our experimental data points through use of linear regression. Now, this method will require us to rearrange the Antoine equation with some basic algebra. We then will create a design matrix and use basic matrix multiplication in order to determine those coefficients. So first we will start with the Antoine equation, which again is log base 10 of our vapor pressure equals A minus B over T plus C. Now, the first few steps here will require me to use some algebra to rearrange the equation, and it might not make 100% sense at first, but it will as soon as we start going through the rest of the problem. So first I will multiply both sides by T plus C. These two terms on the right will cancel out, so we will be left with T plus C times the log of P, and from here going forward I will write this as the log of P, so I will take away the base 10, but it is important to remember that we do have the log base 10 of our vapor pressure. So I have T plus C times the log of P equals A times T plus C minus B, since these two cancel out. So from here what I'm going to do is multiply the terms throughout the entire equation. So I will have T log of P plus C log of P equals AT plus AC minus B. Now, you may notice here that our last term on the right side of the equation is just some fitted parameter, this AC minus B term. So what we can do here is just refer to this term as just any constant. So I will be calling this D. So this term here will be called just a constant D. So now what I'm going to do is subtract this C log P term over and rewrite the equation. So I'll have T log P equals AT minus C log P plus D, our constant. So now we have set ourselves up in order to create a design matrix. So I will go ahead and rewrite the equation that we were just left with. So T log of P equals AT minus C log of P plus D. Now, our design matrix will consist of our experimental data values for both our temperature and the log of our pressure values, and our third column will just be a column of 1. So it'll look something like this. So we'll have our temperature value, so T1, T2, all the way down to our last temperature value, Tn. Like I said, the second column will be our vapor pressure values, and we'll have to take the log of that. So it'll be log of P1, log of P2, all the way down to our last vapor pressure value, log of Pn. Now, since in this equation the log of P has a negative sign in front of it, we will actually need to bring that sign into the design matrix. So we'll have negative here, and throughout the rest of the matrix. And like I said, our third column here would just be a column of 1s. So we'll have 1, 1, 1. And we will be multiplying this by a vector of our unknown coefficients, so the A, C, and D terms. And this will equal a matrix consisting of our T log of P term. So we will have T log of P1, T log of P2, all the way down to T log of Pn. Now, here what I like to do, and this helps me out, is I like to label the dimensions of each of the matrix here. So here we have an n amount of rows and 3 columns. So this matrix here will be an n by 3. Now this matrix here has 3 rows and just 1 column, so it'll be a 3 by 1 matrix. And our last matrix here has n rows and just 1 column, so it'll be an n by 1. Now, what you'll notice here is that we can't really do much because we have an unequal amount of equations and unknown coefficients. We have an n amount of equations and 3 unknown coefficients. So what I'm going to do in a minute is take the inverse of our design matrix. However, I can't do that because our design matrix is not a square matrix. It is an n by 3 matrix. So what I'm going to have to do is multiply the transpose of the design matrix by both sides. But before we do that, we're just going to refer to each of these matrices as their independent variable. So we're just going to name each of them. So the first one I'm just going to name X. The second one I'm going to name V. And the third one I'm going to name Y. So this will leave us with X times V equals Y. Okay? Just going to erase this just to give myself more room here. Okay, so again we are left here with xv equals y. And like I said, what I'm going to do is multiply by the transpose of the design matrix on both sides. So here we'll have, and just before I do this, so we don't have any confusion here, I will be denoting the transpose of the design matrix as x to the t. So multiplying by both sides, we'll have x to the t x times v equals x to the t times y. Now here we actually run into something pretty cool, and this is probably the neatest thing about this example. So what we're going to have here when we multiply the transpose of the design matrix, it is actually the complete opposite dimensions of the original matrix. So what we'll have here is actually a 3 by n matrix multiplied by an n by 3. Excuse me. An n by 3. So this will yield a 3 by 3 matrix. And our V matrix is still a 3 by 1. And our x to the t matrix, again, is a 3 by n multiplied by a n by 3, or an n by 1, excuse me. So this will yield a 3 by 1 matrix. So pretty cool there. So doing this, since we have a 3 by 3 matrix for our design matrix, this then turns this into a square matrix. So we can now take the inverse of the design matrix. So I'm going to go ahead and take the inverse of the design matrix and multiply that by both sides. So taking the inverse, we'll have x to the t x to negative 1 times x to the t x times v equals x to the t x to negative 1, again the inverse of the design matrix, times x to the t y. So what we notice here is that actually this part right here is what is known as an identity matrix. And what this matrix is actually a matrix with ones down the diagonal and zeros everywhere else. So I'm going to go ahead and write that in. So because of this, we can completely ignore this part of the equation. So because of that, because we can do that, it's hard to kind of see. So I'm just going to give you a visual of what this looks like. So again, ones will be down the diagonal and zeros everywhere else. Thus, we can ignore this entire identity matrix. So we are left with, go ahead and erase this. We are left with just this equation, which is V equals the inverse of our design matrix times the transpose of our design matrix times the Y matrix. And V is a vector of our unknown coefficients A, C, and D. So getting this equation actually allows us to determine the coefficients of A, C, and D. So now we will go into collaboratory in order to be able to calculate these coefficients.
All right, so now that we are back in collaboratory, the first thing that we will need to do is code in our design matrix. So I will be denoting the variable x for our design matrix as I have done previously. So xv equals y, with x being the design matrix. So since our design matrix is just simply a combination of 3 columns, we can use the command np.c. And the 3 different columns, again, the first column will be the temperature values, the second column will be the negative log of our pressure values, and the last column being just a column of ones. So we'll have our temperature values, negative log of our pressure values, and I can use this command in order to get a column of all ones. I will set that to the values of t. So What this command here at the end does is it allows me to have a column of all ones with the same sizing as the temperature values. So I'll go ahead and run that. And now what we need to do is calculate our V matrix, which is contained of the AC and D coefficients. So if you can remember, the V matrix is equal to the transpose of our design matrix times our design matrix. You take the inverse of that and multiply it by the transpose of our design matrix times our Y matrix. So I'll go ahead and calculate that. And in collaboratory, when doing matrix multiplication, we have to use the add symbol, so I will be using that going forward. So our transpose of the design matrix times the design matrix, I will be using this command to take the inverse. Okay. And then again, this will be multiplied by the transpose of our design matrix times the Y matrix. Okay, and the Y matrix, if you can remember, is just our temperature values times the log of our pressure values. So we can go ahead and add that in. So temperature values times log of our pressure values. So as you can see, this returns us an array with 3 different values. Now, like I said before, this equation, if you can remember, is equal to our V matrix, and our V matrix contains the AC and D coefficients. So these are A, C, and D values. However, what we need for the Antoine equation is the A, B, and C coefficients. Now, if you remember at the beginning of this problem, we said AC minus B equal to D, the constant D. So all we really need to do in order to determine the B coefficient is rearrange this equation. So AC minus D will then equal B. So we can go ahead and calculate our B here. However, first what I'm going to do is unpack this array into its respective values. So our A, C, and D coefficients. So we'll have AL to denote linear regression, CL, and DL. Okay, go ahead and run that. And now we can go ahead and calculate our B coefficient. So we'll have AL times CL minus DL. Excuse me, this is a multiply. Times CL minus DL. We'll go ahead and set that equal to our B. So BL. Okay, now what I'm going to do is just write out our A, B, and C coefficients and return them so we can see their values. So we'll have AL, BL, and CL. All right, so there we have it. These are our A, B, and C fitted parameters for the Antoine equation that we have found through linear regression. Now what I'm going to do is plot our model, the Antoine equation, with these A, B, and C coefficients that we found through linear regression. So I'll go up here to our plot and add in fig dot add another scatter plot, and our x values will still be equal to our temperature. However, this time again our y will be equal to the Antoine equation with our fitted parameters for the linear regression. So we'll have y equals AL minus BL divided by CL plus T. And we will go ahead and set the mode equal to lines again. Okay, and the name of this will be Antoine linear regression. Okay. Okay, so like you can see, we'll go ahead and zoom in on the plot here. So there isn't much deviance between the model we have plotted for the linear regression and the model we've plotted for the nonlinear regression. So, however, what you can see is that there is a straight line connecting these data points in the middle of this plot as if there's some sort of a gap between those points. However, we know that this is not really a realistic scenario because the Antoine equation calculates vapor pressures for any given temperature value. So there is something that we can do to fix this. So Instead of plotting our temperature values, what I'm going to do, or our temperature values from our experimental data, what I'm going to do is just plot temperature values just for the sake of plotting. So I'm going to add in a variable name called tplot. And what I'm going to do is use a command called linspace that will linearly space out our temperature values. So do np linspace. And we will be plotting these values from the minimum temperature value that we have to the maximum temperature value. And we'll be plotting with 100 data points. So I can do np.min of our temperature, which will take the minimum temperature, and np.max, which will take the maximum, again 100 points. So now that we know this, what we can do is we can go ahead and change the settings for our plot. So we can change, I will go ahead and do it on our nonlinear regression model first so we can see the difference, and then I'll go ahead and do it to our linear regression so that we have a realistic model for both of them. So I'll have tplot and tplot there. Okay. So if we zoom in here, well, we don't really need to zoom in. We can see it from out here, but as you can see, there is more of a curved line here for the nonlinear regression, which is more of a realistic real-life scenario. So I'll go ahead and add in this tplot here for the linear regression as well. Okay, and there we have it. So we have now determined the A, B, and C coefficients for the Antoine equation through both nonlinear and linear regression. So that concludes this video. Thank you.